Hello, everyone. So I think we can start now. So welcome to another week of the Indian Machine Learning Reading Group. Today we have with us Onkar Kishore Susladkar. So he is a machine learning researcher at Yellow.ai and has been primarily working on the optimization of LLMs, building text-to-speech synthesis for low-resource languages, and building systems for direct voice-to-voice understanding. His area of interests are mostly in continual learning of diffusion models or LCR models, and he's also open to research collaborations. If anybody wants to chat with him, they can contact him after the talk today. The paper that he'll be presenting today is called Textual Alchemy, CoFormer for Scene Text Understanding, and this was published at WACV this year. So, Onkar, the stage is yours. You can start.
Yeah, let me share my screen. Okay. So, yeah, so my screen is visible.
Yes.
Yeah, hello all. Good evening. So I'm Onkar Susladkar, and so today I will be presenting this textual alchemy, so co-former for syntax understanding. So this paper is mostly like application-based, new architecture-based paper actually, uh, where we discuss like areas of understanding the syntax images basically mostly. And yeah, this paper got accepted at WACV 2024 this year oral actually. And yeah, so let's talk with first like what is syntax images basically. So syntax images, as you can see in the in the figure, this figure. So the images which are endorsed in the any natural scenes, or which is endorsed with some occlusions with the natural scenes, such as like if we say Starbucks image or this football image. Basically football is written in the, basically this is a Chelsea club football, this thing, some capistrano written. So these images basically are basically the thing are basically natural scene text images basically when we say. So there are two different types basically. One is the natural scene images, and one which we generate basically, or synthetically generated scene text images basically. Yeah, let's understand what are the syntax understanding basically, or STU basically. What does it mean? So so generally syntax understanding comes into the three pictures basically. One is the syntax detection, as you can see in the figure one, like the syntax detection is there. Then there is something called after detection. There is a syntax recognition is also there. So syntax recognition, given an image, like what is written in that image basically, so that is the syntax recognition. So again, the syntax recognition comes under like lot of different aspects. Like one is the OCR and OCR imaging, document analysis, and table parsing, and all those things basically. So that comes into the syntax recognitions and basically syntax detection. Another second aspect is basically the syntax editing basically. So in which what we will be dealing with in this paper actually. So syntax editing is nothing but the given a normal image basically, if you see in the Devanagari, and some artistic style image basically. So we have to get the style of the uh, so we have to so basically the targeted text image basically will get the style of the artistic image, or the style image with the preserving the background and the foreground basically. So that's nothing but the syntax editing, or we can say syntax style transfer basically, as we are transferring the style of one image to another basically, for the preserving the background and the foreground. And second is the visual translation and the visual language translation. So when we use the Google Lens basically, and we keep that Google Lens in front of uh, any signboard or billboard basically of our unknown language, and then it translates basically. So that is basically the visual translation actually when we say. Yeah. And yeah. So for this thing basically, like for the understanding syntax basically, syntax images, basically syntax recognition, syntax editing basically, we come up with the some novel model basically. So this novel model is nothing but the co-former. So from the name itself, we can conclude that what is co-former. So it's a convolutional Fourier transformer basically. So this model we have derived from the basically from the PVT basically, like pyramidal visual transformer basically. This architecture is similar to that. We will not say exactly, it is similar to the that architecture. So let's go deep dive into what it looks actually, what makes it different, and why it performs better in this in the area of basically the syntax, basically syntax understanding. Yeah. So let me come firstly with the go with the CoFormer block actually. So CoFormer block comprises of basically normal KQV basically, followed by basically self attention. We call it here MCA basically, multi-edit channel attention, followed by some inverse FFT and normal add normalization, and again to add the nonlinearity and the extra learnable parameter we call a C block, and normal basically how it is in the basically PVT basically in the pyramidal visual transformer. The thing is, the main aspect of this CoFormer block is nothing but the what we are doing extra here. Basically, the thing is, so we are passing this key query and value from first the 2D FFT basically. So why 2D FFT? So one is along the channel, so one is along the height and one is along the width actually. So we are applying the 2D FFT on the spatial dimension basically. After passing the 2D FFT, we are passing it from the convolution block actually to get the to learn that 2D FFT is basically 2D FFT transformation. And if this key query value, we are this three vectors basically we are passing it to MCA. So MCA is nothing but it's the replica of the we all know the self attention basically, multi-edit self attention. So we call it here as a multi-edit channel attention. So how channel attention? So let me explain. So we get some some shape like for the key we get the some shape like height, width, and some channels. For Q also we get height, width, and some channel, and for V also similarly we get some height, width, and channel basically. So we multiply first K and V, as we all know in the that's how we multiply in the self attention also. So we multiply key and query, basically K multiply by query. And what we are doing basically here, we are doing the batch multiplication basically. And how we are doing the batch multiplication in such a way that basically, let's say if you have some basically key dimension, we will permit that key dimension in such a way that to make the C comma HW, which will get multiplied with HW comma C basically, so that we get the some shape something like this basically. When after the batch multiplication we get the some shape like C comma C basically. This C comma C is nothing but the our channels basically, and on top of that basically we apply the softmax basically along the C1 dimension basically, or the last dimension we apply the softmax. And this softmax this vector basically, or this flattened tensor basically, we again we batch multiply with the value dimension basically value we multiply with the value, and we get the basically the probability distribution across the channels basically. So unlike when we talk about even with the squeeze and excitations, we get the similar result. But here we will be applying every channels basically, every channels to every positions in the every position in the spatial dimension actually. So that's how we make it pretty novel actually. And with this basically we can able to learn a very diverse feature, basically very diverse feature map, which we required for the syntax understanding actually. When so this kind of architectures we can use in the basically occluded occlusions, or mostly to get the diversification of the background and all those things basically. So that's how we talk about basically, this is the basically MCA block basically. And after this basically we concatenate along basically all the heads, we concatenate it. So we deal here with the 8 heads basically. So all the 8 heads we concatenate and we get the like something some C multiply by 8 basically the feature map basically here.
Onkar,
And
there's
we
a
pass it.
question.
Yeah.
Do you want to take it? Yeah, Apurv, go
Yeah.
ahead.
Hello, can you hear me?
Yes, I can hear you.
Yeah, a very basic question. So what's the
Yeah.
input of this block? What does the input look like?
Okay, so input is the 4D input here,
And
four-dimensional input.
these are pixels, or are these spectro, or are these spectral?
Uh, Basically, this is a 4D input, basically, which
Mhm.
we will be. Yeah, let me explain. So this firstly, what we do basically. So there is a image. Firstly, we will get the image. This image we will pass it from some convolution block basically to get some C comma HW basically some this 4D input actually, and this we will pass to our CFB block, that is the CoFormer block.
I see. Okay,
Yeah,
thank you.
yeah. And yeah, for every, so one thing is noticing that like for after every three CFB block, basically we are downsampling it by h by 2 w by 2, and similarly channels we are multiplying it with the 4 basically. So if currently if the initially the channels are 64, so C1 will
Hello.
be 64.
Uh,
Yeah, hello.
yeah, sorry,
Yeah,
sorry to interrupt. I also have one question. Like,
yeah, yeah.
first of all, what is the, I mean, what is the vision behind doing this 2D Fourier transform? And the next
Yeah,
question is, yeah, and the
yeah,
next
yeah.
question is like, you're doing the convolution. I mean, you're doing the query key attention on the sequence of channels, right?
Yeah, yeah,
So
sequence of
along the
channel. Yeah.
channel dimension. So what is the, I mean, intuition behind that? Like doing along the channel dimension and not along the height and width dimension.
No, basically we have to get the we have to get the prioritize of the across the channels, right? When we consider basically the normal convolution, right? Generally convolution applies in the basically the spatial dimensions actually. We get the aggregation of the all the spatial dimensions. But unlike when we talk about the channel dimensions, so there is no basically there is nothing how the channels are being learned basically, like which channel is more important or not basically. So that doesn't have basically. So when you talk about the squeeze and excitation paper, so you might be knowing squeeze and excitation paper, right? uh, SQNet.
No.
Yeah, so basically, yeah. So in SQNet, basically, so basically in the squeeze and excitation is the paper is something like we apply the channel-wise attention actually in that. So why channel attention? Basically, when we apply the convolution, so generally convolution applies in the spatial dimension itself. So we can get the aggregated features for the basically in the spatial dimensions. But when we talk about the channel dimensions, we don't know what weightage of for the which channels we should perform actually. So for that, basically, we generally mostly we have done in the channel dimension basically. I hope this clear your doubt.
Yeah, yeah. So and the reason for Fourier transform FFT. That's it.
So yeah. So that I will be coming in afterwards actually. Yeah,
Okay.
that I am
Okay.
saying.
Okay.
Yeah.
Yeah. Thanks.
Yeah. So the main reason to apply this for basically 2D FFT. So I will conclude in this slide actually. So as you can see, basically this is our input image. So Delhi and all those things, some returns basically. So when we get the Fourier, why we apply the Fourier dimension? So when we apply the Fourier transform, we get the distribution actually. So frequency distribution along the spatial dimensions actually. Okay, as we take the 2D FFT, we get the frequency distribution along the uh, basically along the spatial dimensions. So when we get the frequency distribution, so we can get the high frequency basically high frequency features and the low frequency features. So to get the when we talk about the syntax, general syntax image, basically if we talk about this Delhi syntax image, so basically this Delhi we can separate out with this high frequency feature and the low frequency feature. We have observed that we can able to separate out the foreground and the background actually, and we can learn the more edge level features actually by doing so basically. When we apply the FFT, basically 2D FFT, so we can get the more edge level features, and we can able to learn those features more easily actually. That's how we come up with this observation actually. So that's why we take the Fourier basically. That's why we adapt the Fourier transform actually here in while computing the MCA basically. This is the main reason actually. Uh, I hope this clears the doubt.
Yeah. Yeah. Thanks.
Yeah. Any doubts till now? Like if like any doubt, like it's fine. We can.
Yeah, another question.
Yeah.
So the convolutional operator, I mean, you're essentially, let's say you convolve two signals. It's
Yeah.
essentially the same as doing multiplication in the Fourier space, which is what the CFB block is
See.
also. So why do we need this extra layer? Because like even if you look at the earlier convolution nets, they used to do this edge detection, and they were like, if we looked at the activations of the earlier layers,
Right.
so why do we actually
Yes.
need?
So yeah. So the thing is basically, so what we observe here basically that, so we can able to basically earlier convolution basically more so basically the first convolution blocks in the ResNet and all those things, they can able to capture some edge level information very widely. But the thing is that when we apply this kind of thing, basically like when we apply the Fourier, basically when we apply the Fourier transform along the channel along the spatial dimensions, we observe that like the learning of the model is pretty fast actually here. So if you go from our paper actually, so we have also given the graph. So in that basically the learning capacity is pretty fast actually. So whatever the results we get whatever the results we got into the basically let's say it requires some 30 or 40 epochs. So the same result we will get in the 5 or 10 epochs actually. So 4x fast results we got actually here.
Thank you. That's very interesting.
Yeah, and even we observe this that like we have trained this not only for the syntax actually. So we have trained this network also for the ImageNet also. Entire ImageNet we also trained, and we got like pretty good improvement over the previous architectures in that same segment of the parameters actually. With the same 48 million parameters, we can able to achieve the accuracy of 88% here actually, and that too in very that too in very fast convergence actually. So that's like what we observe in this while basically while implementing this CoFormer actually. So yeah. Yeah, so this is the basically this is the these are our Fourier projection maps basically. So basically we nothing but the activation map you can say basically. So these activation maps are from a ninth layer actually, from the 8th and ninth layer basically respectively. That's how we capture this Fourier projection maps. Yeah, when we talk about like say we did the large scale pre-training also like for the CoFormer. So we did the large scale pre-training. So what we do basically, so we apply two things basically. One is the mask image modeling basically. So MIM we say mask image modeling, and second is basically the syntax recognition basically. So what we do basically, we take the CoFormer, we we first reshape, and we apply two heads basically. So one head which do the syntax recognition. So we transpose and we pass it from by LSTM. So we can also use we also use here transformer also. So but yeah, we feasible to use by LSTM, and the normal CTC based decoding. We apply the CTC based laws, and plus we also did the something called mask image modeling basically to complete this basically patchy noise basically to complete the mask region actually. And we combine all the losses basically, the basically adversary basically GAN loss basically, the generative adversarial loss plus this syntax recognition loss to optimize the CoFormer basically. So this we did the last skill pre-training along over the 10 million images actually. So yeah, so for this pre-training basically we have introduced the two main data set. One is the syntax pre-training data set, which is in the Devanagari, which we call Textverse10M-H actually, and second is the syntax pre-training English basically, which is the
So
Textverse10M.
one question, like
Yeah,
in the GAN, so you said that you had used GAN laws for the CoFormer training, right? So did you use a
right.
discriminator? Yeah. So
Yeah,
you
discriminator.
just
Patch gain discriminator. Yeah. We haven't shown here, but yeah, it's a normal patch gain discriminator
so
plus L1 loss basically.
and the parameter of the discriminator is of the same size as the CoFormer, or like I mean
No, it is it's small. It is pretty small actually. It is
small
like
to
nearly it's like in 1.2 million actually. It's very small actually, just
okay.
to
So that's also
adequate the loss feature. Yeah,
okay. Okay.
yeah.
I see.
Yeah, this thing we haven't shown in this figure actually while making the PPT, but yeah, this all the thing if you read in the paper, so we have written in that actually in the supplementary sections basically we have given in-depth review for the pre-training, how we did the pre-training and all actually. Uh,
Okay.
Even in the
Thanks.
in our GitHub actually we have given that actually. Yeah. So yeah, these two data sets
So,
are
hello.
yeah. Yeah.
Yeah. So, can you please explain the intuition behind the mask image modeling?
Mask image. Yeah. So mask image modeling is nothing but the basically to get the that yeah. So the intuition is the same way. Basically, it can able so basically it can able to capture the fine grain features actually. That's what the thing for the mask image modeling actually. So with with the syntax recognition, basically we can able to capture like what exactly things are written, but to capture very fine grained features, if you say about like the structure, basically the structure of image, or if there is some occlusion, or if yeah, so this image is pretty simple. But if you go with the this kind of images, basically very where the syntax as well as the background is very difficult actually to for even for the human perspective. So for that, basically we use this thing basically to get the more fine grained features actually,
Yeah, and
to
how
learn
did
more
you
fine grained
generate
features.
the and how did you generate the mask and how is this
Yeah,
pipeline
yeah, yeah.
working?
So yeah, pardon. So last question
Uh,
I.
yeah, how is the pipeline of this mask image one? Means how is the
Yeah,
output
yes.
and the
Yeah, yeah. So we take the first input. We input basically. First we take the basically image basically. Let's say of some 256,128 dimension. And what we do basically, we randomly patch the 40% of the area basically. We randomly patch it actually. We have the randomization function, and we randomly patch the 40% of area actually. So we detect the basically where the syntax is, and we randomly mask that parts actually. That's it actually. It's normal masking basically. 40% we randomly mask it actually.
okay? And how is the
Yeah.
output on target?
Yeah.
Means
This is
prediction
the out.
target. Yeah.
Yeah. This is the target
Okay.
actually.
Okay.
Yeah. Yeah.
Okay. So okay. So basically the
It's a
co-former is
self-supervised.
haha. So
Yeah.
basically the transformer has to means reconstruct the input.
Yeah. Yeah. Exactly. Exactly. Yeah. Yeah.
Yeah.
Exactly. Reconstruct the
Okay.
input. Yeah.
Okay.
And with the reconstruction, we have also added this syntax recognition also loss actually to it.
Yeah.
So
Sure. Yeah.
that's how it become more diverse actually. So
Okay.
that like it can able to learn the more fine grained features, as well as it also learns the features for the what exactly things are written actually there.
Hmm. Yes. Right.
And this is a data set basically, that's what we use actually. So and this is publicly available, so 10 million images. So this is currently publicly available, so you can fill the forms and you can get the data set actually. So we will provide you link. Yeah. Yeah.
I have a
And
question.
yeah.
Sorry.
Yeah, nothing. Yeah,
Uh,
yes.
y- for the mass image modeling stuff, why do you
Yeah.
need a discriminator? I mean, it's just simple self-supervision.
Yeah, so basically the thing is when yeah, if even if you take the normal L1 loss basically, or L2 loss basically between the basically
Mhm.
the ground truth image and the predicted image, so that can also work actually. But when we use the discriminator actually, so it doesn't tend to get the mode collapse actually, what we saw actually. So the GAN based architectures are more better in the reducing the mode collapse, right? Like if you talk about normal taking the L1 loss between the image and the this thing basically. It's just a
So
normal pix to pix thing actually. Yeah.
I
why
think
Pix
would
to
we?
GAN.
due to the reconstruction thing, the GAN has come to the picture.
Yeah.
Yeah, I mean, see, you're just basically predicting the missing pixels.
Right. Missing pixels. Yeah.
So I could have done that with simple, uh, like with a masked multi-class, multi-label sort of a setup, right? Uh,
Uh,
like
Multiple as
basically,
in.
like if for every missing pixel, I predict what value it should be.
Oh, okay. So you mean to say like you will be predicting in such way like how the VI like basically when we train the basically VIT or something like that,
Yeah.
right?
So why do we need like a adversarial setup here? That I don't understand.
Yeah. So basically to capture basically by doing so basically you will not get the exact yeah, so let me explain. So this basically when
Mhm.
you yeah, so what you do basically, so when we get the over the distributions, right? So when you only if you don't apply this adversarial setup basically, so basically what we observe is that like yeah, we have also gone through the same way actually. So instead of not predicting in the adversarial manner, we just only predict the basically the patchy, basically what the patches are there basically, that specific value actually. But instead of going that basically, we are not able to capture this out of the boundary features basically in that actually. You're getting like what are the mask region is not there. So that features is it is missing actually in that thing actually, what we have observed in this while making the experiment. But
Yeah, but
yeah,
why would it do that? Like, I mean, basically, most self-supervision methods work like this only, right? Like it's same as BERT for text.
yeah,
Basically.
basically mask yeah, basically we have to predict the mask
It's
token,
within the
basically
same.
what are the things are there. Yeah, right. Yeah, but I don't know, like we didn't observe the similar patterns over this actually when we apply adversarial training over the uh, basically the by predicting the separate tokens actually. Again, one more thing actually here, if you want to predict in this in that way actually, so we have to convert that into the basically the list of tokens actually. That image we have to convert into list of tokens, and then we have to take the token level loss actually in that actually.
I
You're
see.
getting right.
Mhm.
So basically, let's say we have to convert basically, let's say the input image into firstly some set of tokens actually, and those tokens basically we have to compute. Again we have to compute the loss basically with those tokens actually. We have to compute the cross entropy loss actually, like which part was missing basically with the mask and the predicted tokens actually.
And
So that
would it,
may again
and so what is a token here? A token could be as small as a pixel, right? Or can it be?
uh, mm, I feel it can be as small as pixel also, or there is one more. Basically, we didn't think of the pixel level, but how we think basically. So basically, we pass the input image from the pre-trained basically dis pre-trained discretizer actually. So we have the discretizer in such way that like VQ GAN basically, VQVA basically discretizer, and those discrete tokens we will directly compute the loss basically for the mask region actually. So that is the one other way actually to predicting those things.
Thanks.
Yeah. Can you just exactly say that what is the loss used? Just
Here,
repeat. Yeah, yeah. For
yeah. So
yeah,
here is the
MIM.
yeah. So MIM is nothing but the basically L1 loss between the input image, basically yeah, the predicted image and the basically ground truth this mask free image basically, and plus the discriminator loss basically, GAN loss basically. That's it.
So there is no GAN mentioned in the figure, I think.
Yeah, there is no the discriminator is not mentioned there actually. Yeah, right.
Okay. Uh,
Yeah.
So
Could you also,
based on the question that Apurva was, I think means GANs or like autoencoder based that VA that you mentioned means to VAs and GANs are mostly known for image reconstruction and all. So I think that
Right,
is the
right, right,
intuition behind using it.
right.
so could you also comment on how you train this? Like what's like the training recipe looks like? How do you do this sort of mix? Like you have a mixture of losses here in some sense.
Yeah.
And
Right.
so what does the training recipe look like? Do you train one loss on one batch first and or how do
No,
you
no,
want
no, no, no.
these
Yeah.
two
So
loss?
let me explain. So let's say if we can say let's say if we have only one image in the batch for to make the simple. So what we do basically, we take the one image. This one image we randomly mask it. Okay, which will be the input for the CoFormer. Okay, this input for the CoFormer, we are having two heads for this CoFormer. After basically after output of the CoFormer, we are having the two heads. One head will go for the one branch which will do the basically syntax recognition, and second head which will go for the upsampling, basically this GAN thing basically. Okay,
Mhm.
and during the training of the generator, we are also adding this syntax recognition loss actually to it.
Okay.
Yeah, that's it. And that's how this pre-training data set, that's how we make actually. So this is the synthetically
So
derived data set actually.
I have one question. Like,
Yeah.
I mean, are all these images containing only single word, or they have multi-word
Yeah,
as
yeah,
well?
yeah, yeah. Currently it is a single word. Yeah. Currently it is a single word actually.
So then, yeah. So why are you using? I mean, what is the intuition behind using bi-LSTM in this case? I mean, can't it be done with just one? I mean, can't it be just a prediction or a classification based approach?
Classification basically, yeah. But the thing is, see, like we will be having lot of words, right? like
So is it
will
a character level LSTM or it's a word level? The
no, no,
bi-LSTM?
it is a character level actually. That's what I'm saying. It's a character level.
Okay, okay,
And
okay.
it is not like a, and it is not predicting the characters also.
Okay, okay.
So it is decoding the CTC basically. It is a CTC based decoding basically.
CPC.
Connection is temporal classification, CTC loss.
So
Okay, I am.
actually,
Oh
this
yes.
is actually this is an interesting question because you're only training on single word images. So
Yeah,
you
yeah,
could
yeah.
have
So
easily done simple classification here, right?
Yeah, if
no, but
it's character
basically
level,
word.
then I can understand it by LSTM why it's required. But if it's a word level classification, I mean prediction, then I think.
Yeah,
So this,
exactly.
yeah, let me explain. Let me explain. So the
Mm.
thing is basically here we are using the, of course we will be doing the at the basically the characters level basically. So this and this is not a autoregressive classification, basically autoregressively basically given the C, we have to predict the A, then given the CA we will predict the L, given the CAL we have to predict the O. So it's not like that. So basically what we are doing here basically, so you might know the CTC, right? Like connection as temporal classification, where we don't have the alignment between the input and the output basically. CTC loss you might be knowing, right? CTC. Anyone like CTC loss?
No. So pardon, just tell me
Hi
what's.
guys,
Okay,
in
okay.
the
Yeah, yeah.
interest of time, I would suggest that Onkar complete his presentation and then maybe
Yeah,
everybody else can
everybody.
ask the questions.
Yeah,
Right?
it is
Yeah, yeah, sure.
pretty interesting actually. So actually, I made this PPT like pretty not so deep dive actually, but yeah, like it is pretty interesting. Like yeah, so you can connect me. We can over a mail or something like that, or we can after this meet we can also connect actually. So I can explain all the process in the pipeline actually, how we did this actually.
Yeah, yeah, sure.
Yeah. Yeah, sure. Yeah, and in between, if you feel any doubts or if you feel any like you can just yeah. Yeah, so these are the two proposed pre-trained data sets actually. So one is for the Hindi, and one is for basically one is for the Devanagari, and one is for the English basically. And this data set it is synthetically generated actually. Again, this is the synthetically generated actually. This is these images what you are seeing. These are not the natural scene. Basically, these are the synthetically generated. And for every image, you are having the specific word actually for it. So that is also there basically. Again, so after the pre-training we after the pre-training of the CoFormer basically we come up with the two downstream tasks basically. So first downstream task what we do basically is syntax recognition actually. So the syntax recognition is nothing but the, yeah, again same similar thing what we what you guys are saying. So given the image, we have to predict the what is written in the image basically, and that this we are doing with the help of the basically the normal autoregressive GPT decoding basically, normal autoregressive way basically. So what we are doing here basically we are passing this image, and we are also taking the lateral connections from the every CoFormer block, and we are combining all those lateral connections with the help of ASPP, that is spatial pyramidal pooling basically. And this concept is from deep lab actually. And what we are doing, this collective features actually we are passing it from the GPT decoder, and this GPT decoder is decoding the what is exactly written in the sentence actually, or what is exactly written in the image actually. So that's how basically it's a similar case, like the probability of finding the next word given the previous word and the image feature basically, that is I basically. That this is a simple syntax recognition actually. And yeah, so we
Sorry,
yeah, yeah,
like why
yeah,
is
yeah.
the name GPT?
GPT is like generative pre-training. It's like normal conventional actually. It's a decoder only transform actually. That's how it's
Okay.
like normal
So
convention wise.
you use
It is not a yeah, yeah, architecture
pre-trained
is that actually.
decoder.
No, it is not pre-trained actually. It is not pre-trained. We just say it like GPT is nothing but the only decoder only transformer. This is the normal convention actually, naming
Okay.
convention. GPT based decoding basically.
Okay.
Character level GPT based decoding. So this code and this model we have taken from the Enrich Karpati GitHub actually, mini GPT basically. So that's how
But
like that.
Okay.
you already had the bi-LSTM for the decoding, right? Why do you need a GPU? Why do you need a transformer again?
Yeah, yeah. So basically here actually, so this is only for the pre-training phase. Okay. This is only for the pre-training phase. After pre-training, we for the downstream task, basically we use the GPT actually. The thing is basically we have observed. So if we don't use the autoregressive decoding, so the ever accuracy is quite less actually.
Yeah, but
Not quite less, like yeah.
even bi-LSTM is autoregressive decoding, right? Or no?
No. Here we doesn't. That's what I'm saying. Here we doesn't use the bi-LSTM autoregressive decoding. Here we use the CTC based decoding. That is
I
the
see.
different actually. Yeah. And better than bi-LSTM, of course, like the transformer is pretty good at decoding the. It's better than LSTMs basically. So that's why I use it normal. Basically,
But
transformer is bit. Yeah.
but the bi-LSTM does autoregressive decoding. It's just the loss which is CTC loss.
Yeah. Exactly.
And so then
Exactly.
why do we need another decoder?
Where?
So why do we need another transformer decoder? We could have just used the bi-LSTM decoder, right?
Yeah. Basically, the thing is here. See, let me explain. So bi-LSTM. So we get some output of the bi-LSTM. Okay. So after getting the bi-LSTM output, so what the CTC, so CTC based decoding, right? So CTC based decoding is not very feasible actually for the long range character, basically long range word basically. For the shorter range word, when we comes up to like up to 20 characters or 15 characters, it is okay actually. But if you have some long range words basically, so in that case basically CTC based decoding is not feasible actually. So what we do actually, so this is only for the pre-training, okay, like whatever we do for the like bi-LSTM and then CTC based decoding loss, basically CTC loss. So this is only for the predicting the, this is for only for the pre-training phase. After what we do basically, after pre-training, what we do actually, so we take the CoFormer pre-trained weights actually, and we only yeah, after we only fine tune basically for that syntax recognition actually with the help of this GPT actually. That's it.
So you're throwing away the bi-LSTM which you trained.
Yeah, we are entirely throwing away the bi-LSTM. We are only taking the CoFormer block. That's it.
But the CoFormer was only like sort of wasn't the
Backbone. It is backbone. Just it's a backbone. Yeah.
yeah, I mean it's the backbone. It gives you the features, right? The core
Yeah,
features
it
that
gives the features. Right.
then how did the bi-LSTM actually help in getting better features? Was that the motivation?
Yeah. bi-LSTM helps to get the better features actually. That's what I'm saying. So we, instead of bi-LSTM, you can use transformer also, normal transformer also. You can use normal transformer. You can even use the normal LSTM also. That's what
You
I'm
could have
saying.
used we could have used anything over here.
Yeah.
But
We can do it. Yeah. To make the things more basically more faster actually. That's why I use the normal basically bi-LSTM basically.
okay.
Yeah. Yeah, we can. Yeah, of course. Like here we can use anything basically. If you say here we can use anything basically. You can use the bi-LSTM, you can use the transformer, you can use the small bird, one transfer block, anything basically here to decode basically to give the cities based decoding actually. Yeah. So that is basically the syntax understanding actually. Yeah. So we also compare with the basically previous architecture, that is AIBNet and Parsec basically. So another, this is also very interesting paper from ECCV actually, Parsec permuted autoregressive sequence modeling actually. So this is also pretty famous area in the decoding techniques actually for the image captioning or anything basically. This is pretty good paper. uh, I will suggest to go through that paper also. It's pretty good actually. And if you see like we achieve from in triple IT 5 case SVT and CSTR 2.5, we achieve the state of the art. It's better than par sequence actually. So that's how we got it actually. Yeah. So these are our again the more two proposed data sets actually. One is the CSTR 2.5M basically, and one is the Akshara 550 actually. So yeah, so these are again our two. So this CSTR is like very complex syntax images where the words is very occluded, and some words if you see like which is uh, in the straight manner. So this is pretty hard data set actually to recognize things actually. And this is our Akshara 550 data set, which is which is this is the natural scene images basically, which we taken the photos from iPhone 12 actually. So that's it. So these are the two data set we propose actually to make it more diversified results actually. Yeah. So yeah. again, these two data sets are publicly available again, so you can use this for benchmarking and all those things actually. Yeah. Second thing, the second downstream task, we called it as a basically LISTNet actually. So the LISTNet is nothing but the, yeah, it's the same again. So we use the CoFormer actually for basically for the syntax editing actually. So let me explain. So what we do here, we are having basically so basically the access, that is the style image basically, and we are having the target image. So what we have to do basically, so we have to transfer the style to the target actually. So this is the main task actually. So what we are here doing here, so what we are doing here basically, we take the CoFormer basically, pre-trained CoFormer. So one branch which is the pre-trained on the English dataset, basically English syntax dataset, and another which is pre-trained on the Devanagari syntax dataset actually. What we do basically, we pass the input xt and xs basically parallelly actually, and here we are giving the query share mechanism actually. It's like normal cross attention thing basically what we are giving here. And after thing basically what we are doing, we are decoding this basically. So we are so we create the data set in such a way that we will be having all the six things actually, like input image, target image, then there is a background image, and then there is a intermediate style transferred image, and there is a final image which is basically the, we are obtaining the basically the style we are endorsing in the basically background basically. So to get the complete style transfer actually. So yeah, so this is the normal thing basically what we are doing here. Like again, like we are passing it from the CoFormer. One CoFormer is again, here we use the bi-LSTM. Again, you can use anything actually here, like uh, transformer, anything basically, like transformer you can use LSTM, again anything. We are passing here. Here also we are doing the decoder thing. Yeah, again, this decoder, in-depth decoder architecture we haven't given here actually. So you will see in this our supplementary part actually. We are decoding the style image basically, and we are decoding the here the background image basically. Again, we are taking the LST, that is the style loss and the background loss. After that thing, we are just concatenating these images, and we are passing it to the decoder basically. That is the stage 2 actually. And after stage 2 basically, we are predicting here the final style transfer image basically. So that's it, the normal, basically this is the final style transfer image basically. So this whole entire pipeline, or entire thing we called is the LISTNet basically. So just the name actually, LISTNet basically. So that's it actually. Second is this is the second task what we do for the syntax editing actually. Sorry, I'm going very fast actually because of time constraint actually. But yeah, uh, yeah, and yeah, of course, like you can connect me actually to be to get the proper understanding. I will explain this entire thing actually with more clearly actually. Because of time constraint, I'm moving it very fast actually. But again, you can mail me, and we can chat over a Google Meet or something to get the more diverse and understanding of this actually. So this is pretty complex concept actually. So here I'm not again, like I'm not uh, pointing out every crucial points actually here. So that's the thing is, yeah, again, like we have come across the qualitative results again, and we got pretty good results in the syntax editing actually. So this type of syntax editing, this is a by basically multilingual syntax editing actually, like English to Hindi, Hindi to Bengali, if you say English to Tamil, English to Chinese, Hindu to English, and English to English basically. So that's how we cross-lingual syntax editing, what we called it actually. And again, these are the basically the proposed synthetic data sets we use, basically the 500k per images basically. So if you see like input style image, target text image, so all those things which are in the set actually. So these 5 things should be in the set to run this pipeline actually. Yeah. Yeah, and this is the basically, let me explain. So why we need the syntax editing actually in more diverse fashion basically. So when we use this normal input image, and we use the Google Lens basically normal translation app, we get this thing basically. If you see like output image, like very patchy effect, and if you see like, a very patchy thing is not very attractive actually. But if we apply LISTNet plus the Google Lens, we get the pretty good actually. Like if you see like the font and the background and the foreground, which is emboss in this image actually, so it looks more attractive actually. So this is the more practical example. So more practical example is nothing but the when you when you go into any Google web page or something like that, and if you translate that, so all the text inside the web page got translated, but the so some images inside the web page that doesn't get translated actually. So this will be the more important for those who want to do the web page translation and all those things, more attractive ways basically. Again, like the some results basically, if you see some results of the editing actually, if you see here, uh, Barclays and Stop and Town Center, we are editing in the more diversified, more educationally, like we can use the LISTNet in the educational PPTs also to make the content to be more attractive actually. If you see like here, PPTs are been we are retaining the foreground and the background actually here. Also in the LISTNet also you can use in the social media memes actually. Here we can see that. So these are the few examples actually what we saw the qualitatively actually for application of LISTNets actually. And in summary, yeah, so this is the summary. Like we introduce a CoFormer basically, which is the again a type of vision transformer actually for the which applies the integrated Fourier transform and the convolution operation. Uh, yeah, again, this we achieve the pretty state of the art results in the both the syntax recognition and the style transfer actually. And we released like nearly five different data sets actually to the open we for the open source contribution actually. So this will bring us the more upcoming more better results for the thing actually, and introducing the LISTNet framework actually. So that's how we conclude the today's presentation actually. Yeah. Thank you. And yeah, again, if you have again, if you I will say like if you have any doubts or anything, so for the time, because of time constraint, I finish it very fast actually. But you can mail me, and we can connect over Gmeet like anytime, like today, tomorrow, anytime, like on Sunday also I'm totally free, and I can explain all the doubts and all those things. That is not a problem. Yeah.
So thank you, Onkar. We still have a few minutes, so if anybody has any more doubts, they can ask.
Yeah. Yeah, this LISTNet actually I've cleared very fast actually, because there are very lot of crucial points actually to explain that actually. But yeah, I think like it will be pretty good like if we connect over a Gmeet or like anything.
So we
But
still
yeah,
have
again,
10 minutes. Do you
Yeah.
have
yeah,
time to quickly go over it?
yeah, LISTNet, right?
Yeah.
Yeah. Okay. So the LISTNet is basically the thing is basically how we are doing. So again, like we will be we are having the pre-trained we are having the CoFormer pre-trained backbones. Okay. So one is for the one is for the Devanagari, and one is for the basically English basically. And here you are whatever you are seeing, right? Q shared basically. Here we have shared the Q. So that is the query sharing mechanism actually. So this query sharing is nothing but we are giving the cross attention actually to the this style branch actually. We are transferring the features from the we are transferring the input style features to the input target features actually. And this thing after we are getting the two outputs basically here. One output we are passing it to the decoder actually, and another we are passing it to the bi-LSTM actually. So why to do this basically, to get the what exactly things are written here basically, to like traffic. Here we see the traffic, and yeah, that's our basically. So we get the two different what exactly things are written here basically, to get the understanding of text inside the target and the style basically. That's how we compute here LETR and LDTR basically, the two losses basically. And again, here you can use any type of architecture. You can use the transformer architecture. You can use anything actually, autoregressive decoding, anything basically. You can use anything. Again, uh, second branch, we are collecting the two things basically. We are intermediate foreground image basically. We are computing the loss between the predicted foreground and the ground truth foreground, as we are having in those five set actually. And we again one loss for the computing the loss between the predicted background and the predicted ground truth background actually. So this is the loss basically, LBG and LST basically.
So
And
how do
after
you
that,
get the, How do you
Yeah,
get
yeah.
the actual foreground for the target text image?
Yeah, so this is the synthetically generated, right? So we are already having that actually.
Oh, I see. Okay.
Yeah. And we are also having this actual style transfer image also. We are also having that actually. And
So,
our yeah.
so your dataset has the input image, the target text image, the
Yes,
style image
exactly.
of it, and the background image of the source, and also the
Yes.
style transfer image.
Yes. And also what is written in that actually in the target image and the input image, what exactly written in the so that two things are also there in the
Great.
this thing
Awesome.
actually. And the thing is like our next step will be like to make it more self supervisedly basically. So so every time we will not get the foreground and the background actually separately. So we will be trying basically the self supervised. So currently I'm working on that. Like if anybody wants to work here, actually we can connect also. So currently my target is to with the self supervision basically, if we can able to do this basically style transfer basically. So that currently I'm working actually. So this is my ongoing current research actually. So if anyone interested, we can discuss more and we can brainstorm the ideas. So yeah. So yeah.
Is there any further question? Okay. Okay, then let's.
So
Yeah.
uh,
Carry on.
so based on the self-supervised thing, let uh, can you say what is the strategy?
Yeah. So strategy will be basically it will be mostly towards the I will be using mostly in the diffusion models only, like pre-trained stable diffusion. I will be using mostly to do that actually.
Okay.
Yeah.
No, means like how would be the training pipeline?
Training pipeline will be pretty simple. So let me explain. So instead of how we do here, yeah. So instead of if so yeah, so if you see here like how we did the mask image modeling basically, so what we will be doing basically, we will be doing basically something called, we will be having entire syntax basically, not the patch of image, not a patch word, basically entire syntax image basically. And that syntax image basically we will mask the basically the word out of it. And that that mask word we will be giving as an input actually to this CoFormer or anything. And with the conditional with the conditional as a what is written there, that we will give as the condition and we will decode that thing basically. So I don't know, like this will be the might be mostly the training strategy actually. So currently I'm
Okay.
still working actually.
Uh,
Just how we what is that called,
so
image basically the stable diffusion for the image in painting. That's how they do it actually with the help of text guided image in painting basically. So the same strategy will be applied here actually. Yeah, it will be like quite challenging, although like it will quite challenging, but yeah, I'm still working on it actually. So I haven't got the very diverse user. So
yeah,
so there is one paper. Yeah, I will share one paper. So there is one paper in this actually. So DIFUT actually, which got accepted in last NeurIPS actually, which is from again some Chinese author actually. So they haven't released the code actually, but yeah, the paper is very good actually. So yeah, so they did similar way actually. So how I was thinking actually.
Could
So I
you
will
also
share.
comment
okay.
on could you
Oh
also
yeah, yeah.
comment on infra setup?
Yeah, setup. Yeah. So for the pre-training actually, so for pre-training we use the 32A100 actually, 80 GB each, with the batch size of 256 batch size. And we use for yeah, so images are pretty small actually. Some images are 128 256, some are 256 128. So that's why. So we use the 256 byte size. And across the with the gradient accumulation step of 24 gradient accumulation steps. So yeah, that's what the our training setup actually, like 32A100 we have used actually for this.
And what was the dataset size on which you trained? Is it
For the yeah, we are having, right, for the pre-training. So for the
Mhm.
pre-training there are 10 million images. So 10 million for English and 10 million for Hindi, that is the Devanagari. So around 20 million actually.
I see. And how
Yeah.
did you generate these training data sets?
So for generate, so there is a one paper from 2015 actually, which is from Oxford actually. So a well-known author called Ankush Gupta actually. So he had given one very good pipeline actually to generate syntax images actually.
So these are synthetic
Yeah,
images.
yeah. These are all synthetic images. Yeah, yeah.
Mhm.
So I want to ask thing is, so right now it is completely supervised, right?
Yeah. Currently it is supervised actually. At least for the syntax style transfer, it is supervised actually.
So why do you need a self-supervised way?
So self-supervised, so that's the thing is, you will not get always. So if you come with the real world data, so real world data will not have the separate background and the separate foreground images, right? Very accurately, it will not. Of course, with the some computer vision techniques, we can separate the foreground and the background, but it will be not so accurate as the that of synthetic, right?
Yes.
Yeah. So this is the main thing actually, to go with the self-supervised with only the target image and the style image. If we can able to get the similar results actually.
Yeah, target and style. So it would still be supervised, I think.
Yeah, basically no, basically input image with the input target image and the input style image. We will be not having all those things, style, basically intermediate style image, intermediate
Okay.
background image, and yeah. So
Okay. Okay.
basically whatever the loss, supervised loss, we are concluding here, we will be not having
Uh-huh.
anything actually.
Okay. Okay. Yeah.
Sorry, I did not understand. So you said before that the intermediate style image was provided in your data set. Is that
Yeah,
correct?
yeah. It is provided actually. If you see here, oh, sorry, yeah, here it
So
is
how
there
was
actually.
that generated?
Yeah, this is generated with the synthetic. That's what I'm saying. These are all
So
synthetic images.
they're basically fitting to synthetic labels.
Yeah, synthetic labels. Yeah,
So
yeah.
you can only be as good as the synthetic labels, right?
No. So with the so what do you mean to say? Like
And
this will
so
be
there must
only
be
good.
some method which has generated that synthetic style
Yeah,
image,
yeah,
right?
yeah, 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 yeah. There is a method actually. Yeah.
So and you're fitting to that method.
Yes. We are fit to that method. Yeah, exactly.
So then why not just use that method instead of your method? Sorry, just asking devil's advocate sort of question.
No. So the thing
Yes.
is basically, so that method is not a neural method actually. Okay. So the thing is basically, so idea is behind that actually. See, like
Mhm.
so while inferencing basically, we will be only having these two basically. Okay, while inferencing, we will be having only the target image basically and the input style image. So we need to convert this style to this target actually, right?
Sure, but your the way that you got your original labels, that also was produced by some unknown black
No, no,
box
no,
method.
no. No. That is not unknown. So basically, we are providing the font actually. So this same font we are providing actually here. We are providing, right? So whatever let's say this eventually is written here, right? So we are providing the same font for this Bengali text also, to produce this same curvature and all those things. So this black box method actually, so see, so this is not a neural method or something actually.
I see. So
So this is,
even the
yeah.
even so basically the how this data set was generated is essentially like a font is selected. Uh,
Yeah.
a
We
font
selected nearly
is
we selected nearly 700 different fonts actually for this.
okay.
Yeah. We have this is totally hard coded actually. So data generation is totally hard coded actually.
Okay.
Yeah.
Thanks. Thanks for clarifying.
Yeah.
Very interesting. Thank you.
Yeah. Again,
Okay, so
in
we are
this again,
almost.
I will say, like this in this, like in the very short amount of time, the
Yeah.
in-depth understanding of paper is pretty hard actually, and there are a lot of concepts actually still. Some I also forgot to mention and all those things basically. And yeah, we can discuss this in some another meet actually. So that will be very nice actually.
Okay.
And even I would like to discuss this thing.
Yeah, it's almost end to the reading group. We are almost
Yeah.
7 o'clock. So let's thank Onkar again for this wonderful talk, and thank you all for this engaging participation. So yeah, I mean that's it about this week's reading group, and we'll again meet in the next week. And all the best
Yeah.
to you, Onkar, for your PhD.
Yeah. Thanks.
Yeah, hopefully we'll have you again once you join
Yeah.
PhD
Yeah.
and have some
Possibly.
more
Yeah.
paper. So stay in touch.
Yeah. We
Yeah.
will have the collaborations. Very good collaborations with all of. I will. I would also
Okay,
like to do.
okay.
Yeah. Yeah.
Okay.
Again,
Thank you, guys.
my paper author is also here, so she is also Gayatri.
Yeah, yeah,
So she's here
Gayatri is also
actually.
there. Yeah.
Yeah.
Okay. Okay.
Yeah.
Bye.
Yeah. Bye. Thanks.